Imagine you hire a team of like 500 brilliant architects to design this state-of-the-art skyscraper.
Okay, that is a lot of architects.
Right, a massive team. But you completely refuse to let them talk to each other.
Oh, wow.
Yeah, you don't let them look at the same master blueprints, and you actually make them all use different measuring tapes. What happened?
You definitely do not get a skyscraper.
Exactly. You get this catastrophic, insanely expensive pile of glass and steel that just, it collapses under its own weight.
A total disaster.
And yet, this is exactly what happens when Fortune 500 companies try to use generative AI without an orchestration system.
Yeah, it really is a recipe for complete structural failure.
Welcome to another deep dive.
Yeah.
Today, our mission is to completely obliterate that idea of the magic text box from your mind.
Because that's the core issue, right? People are still so stuck in that mindset.
The atomic query, yeah. Where you just type a question, hit enter, and assume this magic oracle is going to spit out the perfect answer.
Which is fine for a weekend project, but it breaks down instantly in an enterprise.
So true. And that is why today we're looking at a landscape that has evolved way, way beyond asking a solitary question.
We are diving deep into the source material from the Enterprise Prompt Orchestration Playbook for Amazon Bedrock.
Right. And the core thesis we are exploring here is just massive.
It really is. It's this idea that to actually unlock these foundation models at a true corporate scale, you have to undergo a total paradigm shift.
A total shift. You have to move away from isolated individual prompt engineering.
Right, the lone developer in a silo.
Exactly. And you have to move toward enterprise-scale orchestration.
What's really fascinating here is how the playbook actually grounds this massive shift.
Yeah, they use a great structural metaphor.
They do. They use this very specific visual metaphor that ties perfectly into your whole architect analogy.
The pyramid.
Yes, they visualize the entire ecosystem as a three-tiered pyramid.
Because, I mean, you cannot have that high-level, super complex orchestration at the top if the foundation at the bottom is literally crumbling.
Precisely. If the base is weak, the whole system fails.
Okay, let's unpack this pyramid because this is basically the map for our entire journey today.
Let's do it.
So the base layer, the absolute bedrock pun definitely intended, is the micro level.
Right. And the micro level is prompt engineering, but not the casual conversational kind of engineering.
Not just typing, write me a poem.
Exactly.
Yeah.
It is the rigorous discipline of crafting the foundation. It's about engineering the specific text and instructions with almost mathematical precision.
Okay, and then we move up to the middle layer of the pyramid, the meso level.
The meso level, this represents prompt
A
management.
governance layer, basically.
Yes, because if you have those 500 architects, or in this case, developers writing thousands of prompts across a global network, you have to manage them.
You need rules.
You need a system to version, control, and deploy them safely. Otherwise, it's just chaos.
Which supports the very peak of the pyramid, the macro level.
Right, the macro level is prompt flow.
And this is where it gets really sci-fi.
It is the active orchestration of complex logic. You're taking those precisely engineered, meticulously managed prompts and wiring them together.
So they can actually execute real-world actions.
Exactly. Querying databases, triggering external services, and even negotiating with other AI models in real time.
So cool. But to really understand this,
Mm-hmm.
we have to start in the dirt, so to speak.
We have to build the foundation first.
Right. We have to start at the micro level. Because if the prompt itself is flawed,
Putting it into a massive orchestration system just means you are going to automate that failure.
automate failure at a blinding speed. That's a scary thought.
It is. Automating a bad process just gets you to a really bad result, much faster and cheaper.
Okay, so the sources are pretty definitive on this. An optimal generative AI prompt in an enterprise environment is not just a polite request.
No, not at all. It is a highly structured data object.
A data object, I like that phrasing, and it relies on 6 precise components to actually function reliably.
6 specific building blocks.
Let's break those 6 components down for you. First, we have instructions.
Right. This is the hyper-specific task description. What exactly are we doing here?
Second is context.
Which is the external background data you inject to guide the model. The situation, basically.
Third is role or persona.
Defining the exact viewpoint the model should adopt. Act as a senior financial analyst.
Right. Fourth is input data.
That's the core material the model actually needs to process, the raw numbers or text.
Fifth, and this one is huge, is the negative prompt.
This is so important. It explicitly states what the model must exclude.
And finally, the output indicator.
dictating the precise formatting structure required for the final answer.
If we connect this back to the bigger picture, you can really see why casually typing "write a report on Q3 sales" into a chatbot just completely fails in a corporate setting.
Because the model is basically just guessing at what you want.
It's totally blown.
Right. When you utilize all 6 of those components, you completely eliminate the model's need to guess.
It goes right back to my analogy of hiring a contractor.
Oh, yeah, the contractor.
If I want a house built, I don't just find a guy with a hammer on the street and say, "Hey, build me a house."
I mean, you could, but it wouldn't end well.
Exactly. I hand him detailed blueprints. That's
Yeah.
my instructions in context.
Makes perfect sense.
I tell him, act as a high-end modern architect, not a rustic cabin builder. That's the role.
Establishing the standard.
Then I have a truck deliver the specific lumber and steel to the site. That's the input
The
data.
raw materials.
And here is where it gets really critical for enterprise AI. The negative prompt. I look the contractor dead in the eye and say, do not use cheap builder-grade materials.
Do not deviate from the blueprint.
Right. Do not cut corners. And the final piece, the output indicator, is how I demand the contractor gives me the final invoice.
You don't want a number scrawled on a dirty napkin.
No. I want a fully itemized spreadsheet. In the AI world, that usually means asking for specific data formats.
Usually JSON.
Let's talk about that negative prompt for a second, because the playbook really harps on it.
That negative prompt is arguably the most vital safety mechanism at the entire micro level.
Really? More than the instructions.
Mechanically speaking, yes.
Yeah.
Because large language models operate on probability distributions.
Right, they're just predicting the next word.
Exactly. They predict the most likely next token. When you use a negative prompt like, do not include personally identifiable information.
Or like, do not mention competitor product.
Right. You are physically shifting the probability weights inside the model's attention mechanism for that specific query.
Oh, wow. So you're changing the math.
You are drastically lowering the mathematical likelihood of those restricted tokens ever being generated.
You are literally fencing the model in.
You're putting up guardrails.
And then going back to the output indicator, you mentioned JSON,
Yes, JavaScript object notation.
which is critical for the orchestration part later, right?
Absolutely vital. JSON is just a standardized way of formatting text into key value pairs.
Like name, John, age, 30.
Exactly. It's highly structured. If your AI outputs a really friendly, beautifully written paragraph,
A subsequent computer system can't read it.
it crashes the pipeline. A downstream server doesn't know how to read a friendly paragraph.
It needs the data.
But if it outputs strict JSON, the next machine in the pipeline can instantly parse it and use that data. The output indicator guarantees machine readability.
Okay, so we have this highly structured 6-part prompt. But the playbook dives into a really wild phenomenon that happens when you feed these massive prompts into foundation models.
In context learning.
Yes, the documentation states that larger models disproportionately gain the ability to learn from these prompts without needing their core programming rewritten.
Right. The architecture actually supports a spectrum of learning directly within the text you send it.
So how does that spectrum work?
It starts at the very bottom with zero-shot learning.
Zero shot, meaning no examples at all.
Exactly. This is where the prompt contains 0 examples. The model relies purely on the vast ocean of data it was initially trained on.
Basically, here are the instructions. Figure it out based on what you already know.
Which is often not enough for complex tasks. So then you move up to one-shot learning.
Where you provide a single example.
Right. You provide a single, flawless example inside the prompt to establish a pattern.
Like, here is a good summary, now write one for this new text.
Yes. But the true power for enterprise logic, the real magic, lies in few-shot learning.
Few shot, multiple examples.
This is where you inject multiple complex examples into the context window.
And what does that actually do?
The model recognizes the sophisticated pattern across those examples and adapts its output to match. It can handle highly complex logical leaps this way.
Okay, I have to pause and push back here for a second.
Sure, go ahead.
The source calls it in-context learning. But the word learning implies a permanent change.
Ah, I see where you're going.
Like, if I teach my contractor how I want a specific, weird pipe welded, he remembers that technique for his next job, right?
Usually, yes.
So, are we actually changing the model's brain? When we feed it these elaborate few-shot prompts, are we permanently teaching it new tricks?
This raises such an important question, and honestly, it is the single most common misconception about foundation models today.
So we aren't changing its brain.
No. The learning here is entirely transient.
Transient, meaning completely
It's
temporary.
completely temporary. To understand why, you have to separate two distinct phases of AI mechanics.
Okay, lay it out for me.
There is training and there is inference.
Training and inference.
When a model is built, it undergoes training. That's a massive, incredibly expensive process requiring thousands of GPUs.
Where they scrape the internet and feed it all that data.
Right. And during that phase, the actual neural weights, the brain connections, are physically updated through a mathematical process called backpropagation.
Okay, so that's the permanent learning.
Yes. But when you are using the model, sending in a prompt, and getting a response back, you are in the inference phase.
And inference doesn't update the brain.
Exactly. Inference is a strictly read-only process. The underlying weights are totally frozen.
Wow, so what is actually happening when I give it a few-shot prompt?
When you provide those examples, you are utilizing the model's attention mechanism.
The attention mechanism.
The model pays intense, localized attention to the examples you provided in that specific text box. It prioritizes them over its general training.
But only for that moment.
Yes. The millisecond that specific API call finishes and the response is generated, the session evaporates.
It's gone.
The model forgets everything. The next query starts with a totally blank slate.
That is wild to think about. It's like that movie 50 First Dates, but for supercomputers.
That is a brilliant way to put it.
Every single time you interact with it, you have to meticulously rebuild its entire understanding of your specific problem from scratch.
Which is exactly why the micro-level engineering we just talked about is so critical.
Because you aren't just writing a request.
No, you are temporarily programming a frozen brain.
Programming a frozen brain. That's heavy.
And the absolute most powerful tool for programming that frozen brain is a technique called chain of thought reasoning.
Chain of thought, or caught a key. The documentation heavily emphasizes this for mitigating hallucinations, right?
It is the silver bullet for hallucinations.
Let's look at the specific retail math problem the playbook uses, because understanding the actual mechanics of why this works is just mind-blowing.
The scenario is pretty simple. A retail store wants to predict weekend footfall.
How many people are going to walk through the door?
Right. The prompt provides the raw data. Monday saw 20,000 visitors. Tuesday saw 21,000. Wednesday saw 22,000.
Okay, pretty clear trend.
And the question is, what is the expected footfall for the coming weekend?
Now, if we do a standard execution, what the source calls the black box model, we just ask the question and demand the answer.
What's the weekend footfall?
But the playbook slaps a massive warning label on this approach. It says, high risk of hallucination.
Very high risk.
But why? I mean, why would a supercomputer fail at basic trend addition? It's just adding thousands.
Because of how it generates text. Remember, as we mentioned, large language models predict the next token.
Right?
They don't have a hidden internal working memory where they can quietly do math on a scratch pad before speaking.
They can't think before they speak.
Exactly. If you force the model to jump directly from the question to the final answer, it has to guess the final number in a single massive leap.
It hasn't generated the intermediate mathematical steps.
So its attention mechanism has no logical breadcrumbs to follow.
It just guesses a number that looks mathematically probable in a sentence.
Which is often completely embarrassingly wrong.
So we have to give it a scratch pad.
Yes.
We basically have to force it to show its work, like a middle school math teacher.
That is exactly what chain of thought execution does. You explicitly instruct the model in the prompt to output its intermediate logical steps before it generates the final answer.
Let's trace how the model solves it when forced to use chain of thought. Step 1. The model generates text analyzing the raw data. It literally prints out onto the page. Monday, 20K Tuesday, 21K Wednesday, 22K trend, increasing by 1K per day.
And right there, just by writing that, the model has generated new context.
Oh, I see. Now, when predicting the next token, it can mathematically attend to the rule it just wrote down.
Yes. It can look back at its own words, increasing by 1K per day.
So it moves to step 2. It determines Thursday and Friday. Following its own written rule, it should calculate Thursday as 23,000 and Friday as 24,000.
Right.
Wait, looking closely at the provided diagram from the playbook, the model's intermediate logic actually calculates Thursday as 22,000 and Friday as 23,000 based on some specific internal assumption in their example.
Which is fascinating, and it highlights the real beauty of the system.
Because we can see the mistake.
Yes. Because the model printed its logic out loud, we can immediately see the exact point where its reasoning might diverge from our expectations.
It isn't a mysterious black box anymore. We can see its math.
Precisely. You can debug the reasoning.
Right. So it reaches step 3, estimating the weekend. The model states its assumption out loud. Assume weekend footfall equals the average of the weekday footfall.
It states the rule.
And then it writes out the math. 20K plus 21K plus 22K plus 23K divided by 4 equals 21,500.
And finally, step 4, conclusion. Expected weekend footfall is 21,500.
By decomposing complex problems into these logical intermediate steps, you are forcing the model to generate its own stepping stones.
You're building a bridge.
The tokens it outputs in step 1 provide the mathematical anchor for step 2. You are using the context window as a highly visible external working memory.
It's an incredibly elegant hack, really. You are slowing the model down.
Forcing it to navigate the decision space systematically.
Exactly. And this drastically reduces the chance of it confidently fabricating an answer because every subsequent claim is anchored to the logic it just successfully generated.
Okay, so that is the base of our pyramid, the micro level.
We've built the foundation.
We've built this magnificent, highly structured prompt. It's got roles, negative constraints, JSON output indicators, few-shot examples, and chain-of-thought reasoning.
It really is a true work of art when done right.
It's highly effective engineering. But this is where the entire dynamic of the enterprise shifts.
This is where things get messy.
Because what happens when our hypothetical enterprise has 500 developers, and every single one of them is independently writing their own beautiful works of art?
You enter what the playbook calls the chaos paradigm.
The chaos. The playbook actually uses that word, and it visualizes this with a diagram that honestly made me laugh out loud.
Oh, the folder diagram.
Yes, it shows a cluttered computer desktop filled with loose text files. One is labeled V1, another is testprompt.txt.
And the universal symbol of developer desperation.
Final, V2 final.
We have all lived in that exact folder.
We really have. But when you scale that kind of ad hoc engineering across an entire enterprise, it degrades violently.
Violently is the right word, because think about it. If a critical application is pulling a prompt from a loose text file on some random developer's machine,
Which happens.
it does, and let's say that developer tweaks a negative prompt just to fix a minor bug.
But they accidentally break the JSON output indicator in the process.
Exactly. Suddenly, the entire downstream software pipeline crashes.
The application just fails silently. The users get garbage responses.
And the worst part? Nobody knows which version of the prompt caused the disaster because there's no paper trail.
Which means the bottleneck shifts entirely from how we write the prompt to where and how we store it.
We have to move up the pyramid.
To part 2, the meso level, governing its scale.
We need prompt management.
So, the playbook dictates a shift to a managed paradigm centered around a centralized prompt library.
It's about treating prompts with the exact same rigor and paranoia that software engineers treat production code.
You would never let a developer push unversioned, untested code directly to a live banking app.
Never. That would be insane.
So you shouldn't let them push unversioned text to an AI model powering that same app.
Exactly. The playbook outlines an 8-step continuous lifecycle for prompt management.
Let's really dig into what happens in this loop, because skipping any of these steps seems pretty catastrophic.
It is. So step 1 is design.
Okay, how is that different from the microtext we just talked about?
It goes beyond the text. It's defining the organizational objective, like what SLA service level agreement are we targeting?
Like what are the latency requirements? How fast does it need to reply?
Right. You have to design for the business need first.
Makes sense. Step 2 is testing and baseline. But wait, how do you even baseline a generative model?
It's tricky.
It's not like traditional code where 2 plus 2 always equals 4.
True. So what you do is establish a golden data set.
A golden data set, what's that?
It's a massive set of historical queries with known, perfectly human verified answers.
Oh, I see.
You run your new prompt against this data set thousands of times, and you mathematically measure the variance.
So if the prompt drifts too far from the golden answers,
It fails the baseline, you don't deploy it.
that prevents those silent failures we talked about. Which leads to step 3, iterative refinement.
Based on that testing data, you tweak the instructions, you tighten the negative prompt to remove any ambiguity you found during testing.
Then comes step 4, which is the absolute backbone of enterprise governance,
Version control.
documenting immutable snapshots. The playbook heavily emphasizes assigning unique ARNs to these versions.
Yes, ARs.
For anyone who doesn't spend their entire life inside Amazon Web Services, What exactly is an ARN, and why is immutability so important here?
Good question. ARN stands for Amazon Resource Name.
Okay.
It is a permanent, unique identifier pointing to a specific piece of data in the cloud.
Like a hyper-specific address.
Exactly. And immutability means that once a prompt is saved as, say, version 1.0 and given an ARN, it can never be changed, ever.
Wait, never. What if there's a typo?
If you want to fix the typo, you have to create version 1.1,
Mhm.
and that gets a brand new ARN.
Ah. So if my customer service chatbot is programmed to use the specific ARN for version 1.0,
It will always behave predictably, even if the engineering team is currently experimenting with version 5.0 in the lab.
my live app is completely protected.
Completely. And if they deploy version 5.0 and it suddenly causes the AI to hallucinate wildly,
The immutability allows for an instant, one-click rollback to the known safe version 4.0.
because version 4.0 still exists, perfectly preserved. Without ARNs, you are just overwriting files and praying.
Okay, that's step 4. Step 5 is monitoring.
Tracking real-time performance metrics in the wild, seeing how it actually performs with real users.
Step 6 is dynamic adaptation.
This is where you inject real-time user context into the prompt, which we will explore in a second with variables.
Right. Step 7 is scaling,
Publishing that tested version prompt to the centralized library so other teams can discover it.
so they can use it safely without reinventing the wheel every time.
Exactly. Breaking down the silos.
And finally, step 8, retirement.
Because the foundation models themselves are constantly updated by the providers.
Right. Claude gets updated, Titan gets updated.
And when the underlying model changes, older prompts might become wildly inefficient or start acting weird.
So you need a governed process to deprecate and retire obsolete prompts before they cause systemic drag.
It's a living ecosystem. You have to prune the dead leaves.
Now, to make this whole ecosystem operational, the playbook details how the Bedrock prompt builder separates static logic from dynamic data.
This is crucial for scale.
It relies on a stack of 3 specific mechanisms: variables, variants, and versions, the 3 Vs.
Let's walk through how these actually mechanize the prompt.
Let's start with variables.
Variables act as dynamic placeholders. Instead of hard-coding a user's specific name into a prompt.
Which you couldn't do at scale anyway.
Right. You insert a variable, usually denoted by double brackets.
So imagine an e-commerce platform with, like, 10,000 users logging in simultaneously.
You definitely don't have 10,000 different prompts.
You have one master prompt in the library, and it says something like, recommend bracket bracket number of accessories, bracket bracket popular accessories under bracket bracket dollar amount bracket bracket for a bracket bracket customer persona bracket bracket who recently bought an iPhone.
Perfect example. The underlying application pulls the specific data for each individual user from the database in real time
It injects it into those variables.
and fires it off to the AI.
So the core logic is static, but the context is infinitely dynamic.
Exactly. That's variables.
Then we have variants. This sounds like A/B testing on steroids.
It is. But we aren't just changing the text of the prompt, we are changing the actual system settings of the underlying model.
The playbook specifically mentions testing temperature and top P.
Yes.
What are we actually tinkering with here? Because it sounds like we're adjusting a thermostat.
You basically are. You are tinkering with the model's creativity, or more accurately, its statistical randomness.
Okay, break that down for me. Temperature.
Temperature controls the probability distribution of the next token.
So if I turn the temperature down,
A low temperature, closer to 0, forces the model to almost exclusively pick the most mathematically likely next word.
it becomes super rigid.
Highly deterministic, rigid, and extremely predictable.
So perfect for writing SQL code or financial summaries where creativity is a massive liability.
Precisely. You don't want a creative accountant.
Good point. But if you turn the temperature up towards 1,
You flatten that probability distribution. The model starts considering less likely, more obscure words.
it becomes creative.
It takes more risks, which you'd want for drafting marketing copy or brainstorming cool product names.
Okay, so that's temperature. What about top P?
Top P is a secondary filter.
How so?
It tells the model to only consider a subset of the most likely words, say the top 90% of probable tokens.
And what does it do with the rest?
It entirely ignores the weird bottom 10% tail of the distribution.
To prevent the output from becoming outright gibberish.
Exactly. So with variants, an engineer can run the exact same text prompt against a low temperature variant and a high temperature variant simultaneously.
Just to see which mathematical setting produces the optimal business result for that specific task,
And once you find the clear winner, you lock it in with our third V versions.
assigning that immutable ARN we discussed earlier.
Exactly.
Okay, here's where it gets really interesting.
This is the best part.
We've mastered the microtext. We've governed it all in a meso library with versions and variables. But a library is just a repository.
Books sitting on a shelf don't read themselves.
Right. How do we take these static, perfectly managed prompts and make them actually do things? How do they pull live data? How do they make decisions?
This is the critical threshold. We are leaving the realm of text generation entirely.
And entering part 3, the macro level.
Active orchestration, or, as the architecture officially calls it, Bedrock flow.
This is where we finally kill the magic text box once and for all.
We transition from a passive answering machine
To an active, agentic workflow.
The guiding philosophy here is thinking in systems, not queries.
I love that phrase.
A flow allows enterprise architects to take those individual versioned prompts and wire them together logically.
It allows the system to analyze intent, right?
Yes, it routes tasks to different AI models based on complexity, reaches out to external servers, evaluates its own work, and even recovers from errors.
All before the user ever even sees a response.
The user has no idea it's happening.
Let's trace the journey of a query through the Bedrock flow architecture diagram provided in the source. Because actually following the logic gates really reveals the insane scale of this intelligence.
Let's do it. The journey starts on the far left. The user query enters the system.
And it doesn't immediately go to a language model to generate an answer, does it?
No, it hits a query processing node first.
And this node triggers 2 parallel prompt actions instantly.
First, an intent analysis prompt.
The system quietly asks itself, what is the true goal of this string of text?
And simultaneously, it hits a context retrieval node looking up the user's specific session history.
Okay, so once the intent is classified, it hits the first major architectural crossroads.
A logic gate asking, is this a simple task?
Let's say the user just asked, what are the store hours for the downtown branch?
That's a very simple query.
So the logic gate routes it down the yes path.
It grabs a basic response generation prompt, sends it to a smaller, faster model. The diagram suggests Amazon Titan and outputs the answer.
Boom, done in a fraction of a second.
Very low latency, very low compute cost.
But what if the user asks something insane, like, if I return the laptop I bought yesterday, can you apply the refund directly to a new purchase of the upgraded model, minus the restocking fee, and verify if it's in stock downtown?
That is decidedly not a simple query.
Not at all.
So the intent analysis flags it as highly complex. The logic gate routes it down the no path.
Bypassing the small model entirely.
Exactly. It sends it deep into the heavy machinery. It routes to a highly capable model, like Claude, which is explicitly designated as the decision-making node.
And here is the real paradigm shift. Claude is not just generating text here. It is acting as an autonomous agent.
The diagram shows Claude branching out into multiple operational nodes.
First, it hits knowledge bases.
Often utilizing RAG, right, retrieval augmented generation.
Yes, to securely search through massive company policy documents regarding those restocking fees.
It's essentially reading the rule book.
Then it hits action execution nodes. It physically reaches out via external APIs.
Let's ground that term for a second. An API application programming interface.
Right.
It's basically how two pieces of software talk to each other across the internet, right?
Exactly. It's the AI sending a structured JSON packet to the store's actual inventory server saying, check stock for item X.
And the server sends a packet back? Yes. Claude interacts with the external API to check the live inventory at the downtown store, and it also interacts with the customer database to verify the original purchase.
It is literally doing the work of a human customer service rep.
Gathering real-time data from 3 completely different disparate systems.
And this is wild. It doesn't just confidently spit out an answer based on what it finds.
No, it does not.
There's another logic gate. And this is genuinely my favorite part of the entire macro architecture.
The feedback loop.
Yes. After Claude synthesizes the policy, the inventory, and the purchase history, it hits a node that asks, valid action.
The system evaluates its own logic.
It checks its own work.
If the API returned an error code, or if the policy document contradicts the user's request, the flow routes backwards.
Then you a feedback loop prompt.
It essentially tells Claude, hey, the inventory check failed. Try searching with an alternate product ID before finalizing.
The system engages in an internal cycle of self-correction.
In a matter of milliseconds,
Only after the internal evaluation node passes the valid action check does the flow proceed to final response generation.
Formatting the highly complex verified answer for the user.
So what does this all mean? You're listening to this and you realize the raw, incredible power of this system. But having a massive flowchart isn't enough.
Not at all.
You have to design the flow to solve your specific organizational problems.
The playbook makes a crucial point here. Your architecture must be dictated by your specific bottlenecks.
There is no universal one-size-fits-all flow.
It depends entirely on what you're trying to solve.
Which transitions us perfectly to the specific architectural blueprints the playbook provides.
They offer 4 distinct patterns.
Let's look at pattern 1, multi-LLM routing.
This blueprint is designed purely to optimize quality and safety through dynamic consensus.
Dynamic consensus. So a query enters the system.
But instead of routing to one model, a decision router duplicates the query and fires it off to 3 completely different foundation models simultaneously.
So like LLM1, LLM2, and LLM3 are all processing the exact same prompt at the exact same time.
Yes, and their 3 distinct outputs flow into an Amazon Bedrock model evaluation node.
And what does that node do?
It cross-references the answers. It identifies hallucinations or discrepancies, determines which response is the most factually robust, and only that winning response is delivered to the user.
It's like having a panel of 3 expert judges evaluating a high-stakes gymnastics routine.
That's exactly what it is.
You aren't relying on a single judge who might have blinked or has a slight weird bias. You aggregate the panel to ensure absolute quality.
Right.
But wait, why would a company do this? It sounds incredibly expensive to run 3 massive models every single time someone asks a question.
Oh, it is expensive. You are literally tripling your GPU compute costs.
So why do it?
You deploy this blueprint in scenarios where factual accuracy heavily outweighs latency or cost.
Like what?
Think of medical diagnostic support, or algorithmic financial forecasting, or deep legal contract analysis.
Oh, right. If a single model hallucinates a clause in a multi-million-dollar contract.
The cost to the company is catastrophic. Quality assurance is the primary bottleneck there, so you gladly pay for the consensus architecture.
Okay, let's contrast that heavy parallel approach with pattern 2, prompt chaining.
This blueprint is sequential. It breaks complex operations down into specialized, linear microtasks.
So moving from the panel of judges to an assembly line.
Perfect analogy. An assembly line.
The initial prompt comes in, it goes to LLM1.
And LLM1 has one singular focused job: extract the raw data and generate a rough draft.
That's it.
That's it. It passes that draft to LLM2.
And LLM2's only job is structural refinement, like take this draft and format it into a professional, standardized report structure.
Then LLM2 passes the structured report to LLM3.
Which applies a stylistic polish, ensuring the tone matches corporate brand guidelines.
Finally, it goes to evaluation and output.
So each AI is a specialist tightening a specific bolt on the assembly line. But mechanically, why is this superior to just asking one really powerful model to analyze the data, structure it, and polish it all in one giant prompt?
There are 2 critical mechanical reasons: context window limits and attention degradation.
Let's break those down. Context window limits.
A foundation model's context window is basically the total amount of text it can hold in its head at one time.
Yeah.
If you feed a model a 50-page document and ask it to perform 3 complex reasoning tasks simultaneously,
It gets overwhelmed.
yes, you trigger a known algorithmic flaw called the lost in the middle phenomenon.
Lost in the middle. That sounds ominous.
It is. The model's attention mechanism heavily focuses on the beginning and the very end of the massive prompt, but it literally loses track of the instructions or data buried right in the middle.
It just forgets the middle part of the book.
Exactly. It gets overwhelmed and drops the ball.
So how does chaining fix this?
By chaining prompts, you drastically reduce the cognitive load for each individual step. LLM2 doesn't need to read the original 50 pages.
It only reads LLM1's concise draft,
Yes. You reset the context window at each station.
which practically eliminates those complex hallucinations.
It is highly effective for massive workflows like AI-driven corporate reporting.
The source briefly outlines 2 other specific blueprints. There's the chain of thought flow, which we kind of explored earlier with our retail math problem.
Right, the architecture diagram for this shows a cascading, iterative logic structure.
Looping back on itself to verify intermediate steps.
It's the absolute go-to blueprint when your bottleneck is complex logical Q&A or generating heavy software code.
And the final blueprint is the few-shot learning flow.
This routes the query straight into a node heavily primed with multiple examples.
And this specific use case here.
When your bottleneck is strict, structured text outputs, like when you absolutely must convert messy human data into flawless JSON packets or SQL database queries.
Because downstream legacy software needs to process it without crashing.
Exactly, it guarantees formatting.
So we are staring at these incredible blueprints. We have the engineered prompts, the managed libraries, the dynamic flow architectures.
It's a lot of tools.
It is. So how does an enterprise architect actually choose which lever to pull?
This brings us to the final strategic framework in the playbook.
The target radar.
Yes. They visualize it as a target radar split into 4 quadrants. It beautifully illustrates that strategic flow orchestration is an exercise in balancing trade-offs.
You cannot maximize everything.
You really can't. If you maximize one, you sacrifice another.
Let's sweep the radar. Quadrant 1, contextual accuracy.
This quadrant demands pacing your information ingestion. If you try to feed 5 years of corporate history into the flow all at once, you destroy accuracy.
Because of the lost in the middle thing.
Right. You have to design retrieval systems that only pull the exact, narrow context required for the immediate query.
Quadrant 2, computational efficiency. This is the financial reality check, isn't it?
Absolutely. It's about filtering noise early, like our Bedrock flow example earlier.
Where we use Titan for simple questions.
Exactly. You use the cheap, fast model for simple questions and reserve the heavy, expensive GPUs for complex logic.
Because if you use your most powerful model for every single, what are your store hours query?
Your cloud computing bill will literally bankrupt the project.
Quadrant 3, bias and error reduction.
Safety and compliance. This requires building in those redundant evaluation nodes we talked about.
The multi-LLM consensus checks, the feedback loops.
Right. Now, it adds significant latency to the response time, and it definitely adds cost.
But it is non-negotiable for enterprise trust.
Without it, you are risking massive liability.
And finally, quadrant 4, user experience.
The human element. Tailoring the outputs dynamically based on the user's intent.
Because if the system is highly accurate but takes like 45 seconds to respond because of massive evaluation loops.
The user experience completely fails, and your employees will just bypass the system entirely.
So orchestration is really about balancing the tension between these 4 quadrants.
Constantly adjusting the dials based on the specific use case.
Bringing this all together, the complete architecture of enterprise generative AI is really a nested, symbiotic system.
It is. At the deepest foundation, you have the micro level.
The engineered prompts, leveraging variables, negative constraints, and temporary in-context learning to manipulate token probabilities.
And those precisely tuned components sit securely inside the meso level.
The prompt management governance layer,
Utilizing immutable ARNs, A/B variant testing, and strict lifecycle deployment.
which acts as the reliable fuel powering the macro layer.
Bedrock flow. Actively orchestrating those components, routing logic, maintaining context.
And interfacing with the actual physical realities of databases and APIs.
Think about where we started this conversation.
We started with the idea of a magic text box.
An atomic query. You asked it a question, and it guessed an answer.
Now look at the reality. You're building immutable architectural components.
You are governing them with the strictness of production software.
And you are orchestrating them through self-evaluating multi-agent flows to execute tangible, real-world operations.
The core takeaway from this entire playbook is that unlocking this technology demands a complete shift in philosophy.
Engineer with precision at the micro level.
Right.
Govern the lifecycle relentlessly.
And above all, think in systems, not in isolated queries.
I want to leave you with a really provocative thought to mull over. Something that builds on all the mechanics we've unpacked today.
Oh, I like where this is going.
We discussed in detail how in-context learning is completely transient. During inference, the foundation model's base weights are totally frozen.
Right, it doesn't actually learn anything permanently.
It just processes the context we provide in that specific moment.
Yeah.
And now we've seen this incredibly robust macro architecture.
The Bedrock flow.
Yeah. The Bedrock flow is handling the logic routing. It's managing the working memory. It's pulling the context via RAG. It's evaluating the errors.
The orchestration layer is doing almost all of the heavy lifting.
Exactly. Which leads to a fascinating implication for the future of the entire industry.
I see it.
If the orchestration flow is handling the logic the safety, and the context.
And the foundation model is just a frozen engine rapidly processing probabilities in the center of it all.
Will those massive foundation models eventually become completely interchangeable commodities?
Wow.
Right. Are we building a future where the true intelligence of an enterprise AI system isn't the underlying language model at all, but the intricate, brilliant orchestration blueprint we wrap around it?
If the model is just a transient processing engine and the orchestration flow is the vehicle, you can always unbolt an engine and drop a cheaper, faster one in. The
Exact.
enduring value, the real intellectual property of a company, resides in the system they design.
The magic isn't in the box.
Hmm.
The magic is in the system you build around it.
That is a powerful realization.
Thank you for joining us on another deep dive. Keep thinking in systems, and we will catch you next time.